Greetings everyone. Our topic for the project is freedom and early depression detection through online social media posts such as Instagram, Twitter, etc. The aim of this research based project is developing an AI based system or model that analyzes the unimodal and multimodal aspects of input data to predict the depression. Next, there are a lot of posts being posted daily on social media. Our problem statement is identifying the early depression by visual or textual data from the content being posted by individual, which give us the insight of existence of early symptoms of depression. Next, our work utilized the different techniques to identify the emotion of depression by unimodal and multimodal approaches. Next, motivation and challenges. There are various challenges as data on social media is very noisy and unstructured, which makes difficult to extract the features and pattern. The motivation of this project is determining the underlying emotion of depression, which helps our society. Next. There were many research happen on this topic. The initial work which were proposed to solve this problem is machine learning based approach, which uses the extracted feature from the phone and sensors and uses the machine learning models such as SVM, Gaussian mixture model, etc. Some work also being done in deep learning based approach which analyze the linguistic and behavior pattern in text as well as in image.
In this project, we collected data from multiple websites to create various datasets that were suitable for the different architecture we were testing. To achieve this, we utilized web scraping techniques to extract images from Shutterstock and text data from Reddit, which we then used to train our unimodal architectures. We made sure to gather a diverse range of emotional content to create a comprehensive dataset. Additionally, we created main dataset by scraping just Shutterstock and used the alternate text to train our final multimodal architecture. Finally, we created inference dataset by scraping social media posts where the text served as the caption for the corresponding image. We evaluate the best architecture trained on the main dataset by testing it on this inference dataset consisting of 20 images and their respective captions. To perform image classification, we utilize 5 different architectures: CNN, ResNet 50, VGG19, Inception v3, and Exception. For text classification, we used BioLSTM, SVM with non-contextualized and contextualized embeddings, and fine-tuned BERT model. Additionally, we proposed 3 multimodal architecture prepared by fusing the best unimodal architecture for image and text classification. These multimodal architectures were designed to combine the strengths of both image and text-based model to improve the overall performance of the system. As part of our efforts to introduce novelty in this project, we created a web-based dataset by scraping social media posts. This dataset is specifically designed to build a web-based depression classifier that could accurately detect signs of depression based on social media posts. Furthermore, we worked on building a multimodal architecture that could effectively process both image and text data from this web-based dataset. By combining the strengths of image-based and text-based model, our goal was to create a powerful depression classifier that could accurately identify signs of depression in social media posts.
Coming to unimodal classification, for image classification, there was several pre-processing techniques were used that were rescaling, share range, zoom range, and horizontal flip. For the pre-trained models, we have used ResNet 50, VGG19, Inception v3, and Exception. Coming to learning rate, the learning rate was set to 0.01. However, to prevent the case of overfitting the model and to keep a check on the redundant update of loss and hence the inability of the model to learn further, the patience for decay is kept as 10 and the learning rate reduces by a factor of 0.5 if there is no significant learning for 10 consecutive epochs. Uh, the optimizer used for our project was SGD for particularly unimodal classification, and the loss function used was binary cross entropy. Next. As we can see the metrics in result part, like for the data one, we have VGG has the best like 0.85 accuracy. After that, Inception, Exception, both are equally good, 0.84. If we come to precision, like 0.85, Exception was the best one. After that, Inception. Coming to the dataset 2, Inception V3 has outperformed almost all other models in all departments. Like we can see, accuracy was 0.82, and the Exception, the second best model, accuracy was 0.80. Apart from that, if I come into F1 score, the Inception F1 score was best, which is 0.85, and the second best model was Exception 0.82.
To find our robust and best performing textual models, we conduct the following experiments. Firstly, we use non-contextual embeddings from fast text to produce server embeddings for capturing the meanings of complex morphological and out of vocabulary words, and then use SVM classifier for our training. Next, we use the contextualized pre-trained BERT embeddings, which is highly contextualized for understanding local semantics better than the non-contextual embeddings, and then again use the SVM classifier for training. And the third model is using the fine-tuned, the third model uses the BERT tokenizer to create our word embeddings, and then you fine-tunes the BERT model to capture contextual information. Next. So these are our various results on the different models we have applied for textual classification. We have used BiLSTM as our baselines. Then, as explained earlier, fast text, BERT embeddings, and the complete fine-tuned BERT model. And as we see, we have a gradual increase in accuracy for the first data set, and similarly for the second data set. Also, I would like to point out that the second data set is is the multimodal data set which has been trained specifically for the textual classification, and the meanings are encoded. I need to say it again. Okay. Uh, as explained, we have the following results. We have used BiLSTM as our baseline model, and then used fast text, the pre-trained BERT embeddings, and the fine-tuned BERT model to perform textual classification. And as we see, there is a gradual increase in the accuracy and corresponding results in both the data sets, text 1 and text 2. Also, there is a decrease in accuracies for the second dataset in comparison to the first one, because the second dataset contains uh, multimodal data, which would, as expected, perform poor on unimodal text classification.
Uh, so now, as we have discussed earlier about the unimodality approach for handling text and images, now let's discuss about the main multimodality based approach in which we are handling both images and text simultaneously. For multimodal fusion, we are using late fusion in which we first extract feature from the images, then from the text, and after extracting features from both the modalities, we then concatenate both of them to find the final decision. Let's discuss about the architecture of our multimodal model. So this is the architecture in which you can see that we have an image and its corresponding text. We individually send it to their respective models. After getting the textual features and image features, we then concatenate them and pass through the softmax to classify the image and text as depressed or not depressed. So for this, we have experimented on three different setups of models. First one is ResNet 50 plus Distilbert. Second one is VGG 16 plus Distilbert. Third one is Inception V3 plus BERT. So out of these three combinations, all of them works very well to understand the context between image and text. But the Inception V3 and BERT outperforms all the other setups with 96.89 percentage, as you can see from the results. Now, as we see, the Inception V3 is best in unimodal for images and BERT is best for text. This also proves that the combination of best unimodal models works best on multimodal as well. So, and our multimodal model is also able to understand the real-time images and text from social media posts with accuracy on inference data is 75%.
An important part of the model architectures being designed is to include and explain the concept of explainability for each of the models designed. Specifically for the task of image classification, we introduce a tool called GradCam, and it is important because during the process of implementing the model, the users need to visualize the features which are being learned. These features, if visualized, are important to improve the architecture as well as the dataset. From the inferred learnings, we can learn a lot about how the model is processing the data. The two key tools which we utilize to visualize the learning are GradCAD and stochastic neighbor embedding plots. In this slide, we can see that we have a heat map. The gradient heat map visualizes the gradients which are being learned. We then overlap it with the original input image, and hence we are able to clearly visualize the patches of the image that contribute significantly towards predicting the probabilities of the areas which were significantly contributing for the final prediction. In this slide, we can see that we have the visualization for a depressed image. That is for a person who is depressed, the model is able to learn well from body posture. And for the second image, where we have to learn if the image is a not depressed image, we highlight over the facial features of the people. The model learning may be distinct for each case of image, and hence it is important to visualize it. The next tool which is being used is stochastic neighbor embedding plots. We extract out the features from the last embedding layers of our fuse model, and as the stochastic neighbor embedding plot plots the points which have the maximum probabilities of being the neighbor to a given point are clustered together. So here we have two distinct clusters which are being formed, clearly indicating that if these feature vectors which are plotted in a low dimension are then further processed, will be able to distinguish as the two categories as depressed or not depressed. Now we will proceed on to the conclusion. The conclusion of this project derives its basis from the fact that we proposed an entirely new dataset. The dataset which was proposed was specifically extracted from the web for the fact that it would be able to generalize well on the new social media post dataset which was designed for inference. Hence, our model architectures and results show that the model was able to adapt well to the content which is being posted online. Apart from that, the novelty which was exploring unimodal classification for the similar task proposed ultimately led to the final model, and the multimodal and the fused modalities with the proposed multimodal deep fusion-based model architecture using BERT and inception-based embeddings was able to perform the best. And the project very well satisfied the aim to detect depression on social media. This technique can further be deployed on web pages to rank the web pages according to the content of depression in it. The next point is future scope. As we discussed throughout the development of this project, the project has certain shortcomings which can be improved in future scope. We can include data from different social media websites as LinkedIn, where it may not be very evident that a person is depressed or not, but through the text which is being posted online, it can be extracted if the person is depressed or not. We can include multiple modalities as audio and video, and then use it with the input image and text to make better predictions. Next, better fusion strategies as attention-based fusion or cross-model retrieval-based fusion can be explored to improve the performance on the basis of different metrics. This also opens the scope of deploying the model through an Android application or a web-based application to detect early signs and symptoms in the user's post or the web pages which are being scrolled by people. So that was it. Thank you.